Hello, this is Ms. Nichols, and this video is on conservation of charge and charging. The essential question for this video is, how do objects end up with an unbalanced sigma charge? Let's start by introducing a new variable, and it's going to be a variable called charge, which we've already been talking about, but we haven't really given it a symbol and units and all those kinds of things. So charge is going to be represented by a lowercase q when you see charge in equations. And the units of charge are the coulomb, which is a capital C. So you might say something, Q equals 4 coulombs, and that would tell me the charge of the object is equal to 4 of this unit of a coulomb. Now, the vast majority of the charged particles in the universe are protons and electrons. There are also neutrons in the universe, but those aren't charged, as you'll see in just a minute. So mostly what we care about is the charge on a proton and an electron, and how having different amounts of proton and electrons in an object is going to control the charge of an entire object. So we're going to say that protons have a charge of positive 1 coulomb apiece. That's actually a little bit of a lie, which is why I put an asterisk on there, but it makes our math a lot easier in this class to just assume that 1 proton equals 1 coulomb. Electrons are going to have the same amount of charge, but negative, so we're going to say electrons have a charge of negative 1 coulomb apiece. And as I mentioned, the neutron is neutral, which means it actually has a 0 coulomb charge, or nothing is in charge. So charge is one of those important fundamental variables that is conserved, like mass and energy are conserved. What that means is that in any closed system, we are going to have the same amount of charge before, during, and after anything happens. We're going to keep the same amount in those systems. One crazy fact is that the biggest system, the system of the entire universe, has a sigma charge of 0. That means that there are exactly as many protons in the universe as there are electrons in the universe. Scientists haven't been able to discover a reason why this has to be true. It just appears to be dumb luck that we're born into a universe where there's the same number of each. And it's a darn good thing, because if we had a significant unbalance in the number of protons and electrons, planets would be ripped apart, life as we know it would never be able to form. So lucky us, we happen to have as many protons as we do electrons. Most smaller objects and systems also start with a 0 coulomb sigma charge. This pen, for example, has protons and electrons in it, but it probably has about the same number of each, because each atom tends to be balanced out. So you add up all the protons, you take away all the electrons, and you end up with a neutral pen. Most things are neutral to start. So we can create a situation, though, on some small systems where the sigma charge is not 0. And we're going to talk about how to do that later on this video, but first let's just talk about what that looks like. So the sigma charge of any system is going to be the total charge of the protons, which are positive, plus the total charge of the electrons, which is negative, or you can think about that as subtracting from each other. So for example, in this system containing these 4 atoms, we have 4 pluses, 4 protons, and we have 3 minuses. So the sigma q for this system is positive 1. There's 1 positive left over. And we would say this is a small positively charged system. The second system has 4 protons and 4 electrons. That's pretty typical of most objects, the same number of each. And that means that the sigma q for this is going to be 0 coulombs, because all the positives were canceled out by all the negatives. Another name for this is neutral. And in the third small system, we still have the same 4 protons, but this time we have 7, it looks like, electrons in there. And so we have a positive 4 minus 7. This is going to give us a sigma q of negative 3 coulombs, which is a somewhat more charged negative object. Objects that are charged can do some really interesting things in the world around us. They're actually really powerful objects. It's a more powerful force than gravity. So charged objects can do some really interesting things. One of the interesting things that you can do with a charged object is that you can push or pull around the subatomic particles in other objects because of the electric force acting between the charges in these objects. So one of the ways you can do this is called polarization. Polarization happens when you take an object that has an unbalanced charge through some reason. We'll talk about how it got that way in a little bit. But we take that object and we bring it near another neutral object. So let's just say we have a negative object there on the left. It's got 4 protons and a whole bunch of electrons, so it's negative. And we're going to bring it near this object on the right, which is going to be neutral. It doesn't look neutral right now because it only has 4 protons in it, but it's going to have some electrons in it as well. So this object on the right, the subatomic particles are going to feel a force from that object on the left. Specifically, the protons are going to be a little attracted, but the electrons are going to be repelled because like charges repel. Except for, it turns out only the electrons can move. That means the protons, even though they're kind of attracted, don't get to go anywhere. But the electrons in this object, and I've drawn it like a conductor, right, so they can actually move anywhere they want, end up being pushed away from that other negative object, and they all kind of pile up on the right side of this object. Now you can see the object is still neutral. There are still 4 positives and 4 negatives, but it has a positive half and a negative half, and that is called polarized. One interesting thing about this is that a polarized object ends up attracting to the charged object no matter what the charge of that object is. And the reason is because that positive half, right, the left half of that object is being pulled towards the positive object, or towards the negative object, more than the negative half is being pushed away because it's closer. There's the same number of charges, but remember that the electric force has an inverse relationship with distance. So because that half is closer, it actually gets pulled harder than the other half gets pushed. So if you bring a charged object near a neutral object, it's going to attract. I wanted to introduce that process of polarization because it becomes really relevant as we start talking about how to actually permanently get charges on objects. Polarization is kind of a temporary movement of charges around in an object, but charging is defined as taking an object that starts balanced and moving electrons on or off of that object so that it ends up unbalanced, right? In the polarization, we didn't actually change the charge overall of the object, but in these processes that I'm going to talk about next, the original object will end up with a different charge overall when we're done. A quick note, remember that only the electrons are moving in or out of the object. If you try to move a proton in or out of an object, you get a nuclear explosion. So we're not going to move protons around in this class. You can do that in more advanced physics classes. There are 3 main ways of charging objects up that we're going to talk about. The first one is one you're probably familiar with from your life, and it's called friction charging. True to the name, it involves taking 2 objects and rubbing them together, specifically 2 insulators. This kind of charging only works if you use 2 insulators, and I'll talk about why in a minute. When you take 2 different insulators and you rub them together, electrons end up transferring from one to the other. So let's say we have 2 insulators, this green one and this orange one, and they're both neutral to start, right? They both have the same number of protons and electrons. They both have a sigma q of 0. But when I rub them against each other, that orange object is grabbing some of the electrons that are near the surface of the green object. And if you count up the charges of those things now, you'll discover that the green object now has 5 extra protons, and so it has a sigma q of positive 5. It got that way by losing electrons, not gaining protons, but it still has 5 extra protons. And then the orange object has gained those 5 electrons, so it has now a charge of negative 5 coulombs. Quick little note, the system didn't gain or lose any charges overall, right? The overall charge of that system, even once those charges have moved around, is still 0 because we have the same amount equal and opposite on those 2 objects. So charge is conserved, but they've been moved from one object to another. So what determines which object's going to gain the electrons or lose the electrons? Short story, it's chemistry. It depends on the materials that are rubbed. Some materials really love electrons and they always are grabby, 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 and other materials really don't care about their electrons and they tend to give them up. There is something called the electrostatic series that tells you how likely an object is to gain or lose electrons when you do friction charging. So for example, rubber whenever you rub rubber on almost anything, you're going to end up with rubber becoming negative and the other object becoming positive, because rubber really, really likes to grab electrons. On the far end of the spectrum, glass really doesn't care about electrons, and almost anything you rub on glass is going to end up taking the electrons from the glass, and the glass will end up positive. So you can use this little diagram to help you figure out, when you rub two random objects together, which one is going to become negative and which one is going to become positive. The second kind of charging is known as contact charging. Contact charging occurs when you have two conductors that have different sigma charges to start. And when you take those two conductors and you bring them into contact, hence the name, what happens is the electrons are going to try to flow around until everybody is sort of balanced out and the object has the same amount of sigma charge on both parts or both halves of the objects. So for example, if I have a sphere on the left that has a charge of positive 6 coulombs and a sphere on the right that has a charge of positive 2 coulombs, think about this from the perspective of the electrons, right? Those electrons on the right would rather go to the left because there's a lot of extra protons over there, right? So when I bring those things in contact, some of those electrons from the right move on to the sphere on the left because there's a lot of extra protons over there. And they just kind of move around and shuffle until everybody is basically as spread out as they possibly can be. And at that moment, the sigma q for each object is the same, and it's 4 coulombs, right? So that left object started at 6, but 2 electrons moved over, and that's why we're at 4, because we added 2 negatives, right? And the one on the right started at 2, but then lost 2 electrons, so we became more positive, or 4 coulombs. You'll notice that charge is still conserved in the system as a whole, because the total charge of the system before was 8 coulombs, and the total charge of the system after is still 8. It's just distributed a little bit differently. Before I get to the third type of charging, I want to mention one more process that it's important to understand when it comes to moving electrons around, and this is something called grounding, which you may have heard of before. Grounding refers to connecting any object to the earth or to the ground with some kind of wire. And when you do that, you basically allow electrons to flow either onto the earth or off of the earth. And those electrons might be used to balance things, they might be used to charge things, but the idea is the earth is so huge, it has an almost infinite supply of electrons, and it can absorb extra electrons without really noticing it because it's so huge. And so that process of connecting to the Earth's reservoir of electrons is known as grounding. So the final charging process is known as induction charging, and this is both the most complicated one and probably the most important one in terms of the real world. Induction charging actually means charging without contact. If you've ever used like a wireless charger before, it uses induction charging, which is kind of cool. So induction charging uses both of the processes we've learned, polarization and grounding, to give a charge, an unbalanced charge to a conductor through a series of steps. The first step is you start with your neutral conductor that we're trying to charge. The second step is we're going to bring a charged object nearby. So this is that polarization step. In that picture, it kind of looks like those protons are moving to the left, but that's not really what happens. We know that only electrons are going to move. What happens is the protons that were on the left basically get left behind by their electrons, and that's why it looks like there's a lot of protons over there. In any case, that conductor is still neutral. It still has 4 protons and 4 electrons. They just happen to be one on each side, or each side is charged. The third step is to ground the conductor. So we take a wire and we connect that conductor to the earth. And when we do that, electrons can go either way. But if you're an electron, you are trying to get away from that big, scary negative rod that got brought nearby. And that's why, in this case, electrons are actually going to flow off of the object onto the ground to get away from that negative rod or negative charged object that was brought nearby. So the electrons from the sphere are now on Earth. Step 4, you just remove that wire. So separate the wire, right? And then what happens once you take away that charged object is the conductor is left with positive charges because we took away all of its negative charges. And you didn't have to touch that conductor to the charged object. In fact, it gets the opposite charge from the charged object, which is kind of cool. And we've been charged without touching those things, and that's why this is induction charging. The concepts in this video are actually really, can be really rich and deep. So I'm gonna just pose a few level 4 questions if you want to add to your notes, put a little bit of thought into this right now. Number 1, does each kind of charging represent an open or closed system for mass? What's your evidence? I talked about it for a couple of the kinds of charging, but definitely didn't talk about that for induction, so you can think about it there. The second thing, will the two objects involved in charging be attracting or repelling each other after each kind of charging, and why? And then the last one is, can you go through that entire induction charging process again from the reverse perspective? What if the object that brought in, instead of being a negative rod, was a positive rod? What would happen during that induction charging process? If you can go through that, then you probably understand all of these processes and concepts pretty well. Okay, please take a few minutes to revisit the essential question in your notes, which is, how do objects end up with an unbalanced sigma charge? So go ahead and jot down some of your thoughts or questions and bring them back to class. Thanks for watching.